I was about to give up, but then I switched the wires over and I put negative polarity on the emitting points, and I threw the on switch on the CRT, and the thing floated up near the ceiling.
Hello everyone, and thank you for tuning into a video that's going to be rather different from what I've done before. Last year in April, I did a mission where I orbited Kerbin using only ion engines. This turned out to be my most popular video ever. It did well in not only the KSP community, but outside of it as well. What I take from this is that there's a lot of interest in ion-powered flight. In that video, I mentioned that there had recently been a flight from a team at MIT of a real-life, fully self-contained, fixed-wing, ion-propelled plane. I was a little bit remiss in my research at the time because I thought that this was the first flight of a self-contained ion-propelled craft in general. It turns out that this first flight actually predates the flight of the MIT team by about a decade. My guest is Ethan Krauss. Ethan is an electrical engineer from Ohio, and he is the inventor of the first self-contained ion-propelled aircraft. Ethan was kind enough to have a conversation with me about the history and technical details of ion-propelled flight. Break that down for us. What exactly is meant by self-contained ion-propelled aircraft?
Since 1950, there have been inventors that have made devices that can either swing around a pole or float up into the air with a very large external power supply, a high voltage power supply. But they were never really, they were just a curiosity, like a science demonstration. And the problem was, most people thought you could just never get that power supply on board the vehicle. If it takes a 200-pound power supply to lift a small toy, it just didn't seem like it was going to happen. And I worked on it for years and years and kept making smaller power supplies and better ion-powered aircrafts. I
found pictures on your site of experiments you were doing. I think I saw some as early as 2002. So
sure.
You've been working on this for a while.
20 years, yeah.
Do you have an idea of about how many different iterations or versions or tests you've gone through in that time?
People might almost be worried about me how many I've done, It's like bags and bags full. I used to, on the early experiments, I had paper bags that were, partially filled with burned out transistors. And I just did, it was kind of like reckless experiments in the very beginning. And then I became more careful and guided about it and used more math. Still, I have a lot of experiments that don't result in a great deal of improvement, and so I just do a lot of experiments.
Yeah, you can't really know if something's going to be an improvement or detriment or just neutral until you try it.
Somebody told Edison they had a great idea, and he said, "Well, just go do it."
Yeah, like I know in Kerbal Space Program, this is the program the process we go through. But in real life, there's so many more variables to deal with. There's so many more things that could go wrong.
Yeah, it gets to the point where you want to glue something together, but the glue keeps failing, or it's too heavy, or you put the glue on, when you remove it, there's like a glue thread, and that can be a problem. So you end up doing this like research project just to get the right bottle of glue, and it can take weeks or months to get the glue just right.
What is the best glue?
Well, I'll tell you, each part of the thing has a different kind of glue.
So you've optimized this to the point of using the exact optimal glue for each part of it. Exact
right amount and exact optimal glue for each part. Almost. It still has room for improvement, but
right.
Everything, every little piece of material on it takes a lot of thought, and you learn the hard way, kind of.
Many of my viewers probably have a pretty good idea of the general level of how an ion engine works, but I think almost everyone could benefit from hearing a more detailed description of how exactly the engine you're using works.
All these sorts of propulsion systems, in-air ones, use a emitter surface and a collector surface. And the emitter surface is made of very small points or very thin wires. And the collector surface is made of rounded conductor. So when you put a high voltage DC between the two surfaces, there's an airflow from the sharper surface to the more rounded surface, right? And in the case of the vehicle that I have, you can't actually see the emitter wires on the videos. What you're seeing are the emitter wire support, horizontal emitter wire supports.
Gotcha. Okay.
So emitter wires mine are so thin that you have to wear mag goggles to see them. You know?
So what are the thin wire-looking things I see sticking up?
Okay, those are very thin plastic tubes, and they support their special dimensions and material, and they support the emitter wire that looks like a cobweb going around above it.
Right.
Those are just supports for that.
Right. So that's just part of the structure that's holding everything together. Ionocraft are solid state. They have no moving parts. Explain to us how that's possible and what advantages this offers.
What's the advantage of a transistor? Well, there's a lot of advantages, as we know. We wouldn't be on the computer today, The way that it flies with no moving parts is that it does have ions that move, but it's mostly electrostatic pull. People often think that you have this corona wire that kind of sizzles and glows and heats the air and rips particles loose and so on. And if you don't do it right, that's kind of what is happening. But if you do it right, you have this thing that's almost silent, and it just releases electrons, and the O2 molecules absorb those electrons pretty silently. Since the collector surface is at the opposite polarity, O2 molecules with extra electrons jump down to that positive surface below. There's an analogy with pool balls. You get some of them moving in one direction, and they knock the rest of the pool balls along with them. But actually having the other pool balls in the way probably reduces the force involved.
Although if you're moving more mass,
you're
getting more force from that too.
You could either move the mass faster, or you could move more of it more slowly.
Find the amount of mass moved and then the mean velocity that you've moved it at, and then you got your force.
Yeah, and how much?
This has got to be hard to measure, though. I guess you could look at the final resultant force, and that's the real measure of if you're improving.
The first 6 years, no, not 6 years, 11 years that I did this, devices were hanging under a postal scale. And I would test, and I would see, oh, gee, I'm getting, 10%, 20, 30% lift, and I would just keep playing with everything until the numbers got better, until the scale would read less and less. And that way I didn't have to, have the thing, have landing gear on it or any of that extra weight, That's how you measure how much force you're getting, how much thrust to weight ratio, right? One of the first times I flew it with legs, I have a video of that published on my site, on my YouTube site. And
which I will link in the comments to this video.
And that one, is one of the first ones where it had legs and tie downs instead of a postal scale over it. And it was kind of cool to see it take off with nothing over it,
Right.
And then people are saying, oh, but it's got tie downs. And before that, I could just fly it with, one safety tether, going
right.
to the postal scale. So, and you can see the thread get all loose, and the postal scale go up to 0.
In Kerbal Space Program, the engine that we have available to play around with in the simulator is based on the engine in the Dawn spacecraft. But they've actually, by several orders of magnitude, they've increased the thrust, presumably for like the pacing of things, so things don't take as long. I don't think your average hobbyist Kerbal Space Program player wants to wait 3 months to do a mission. The stats that we've got to play with are, we have a 250 kilogram engine, and it gives us 2 kilonewtons of thrust.
Okay.
Which is several orders of magnitude more than what the Dawn spacecraft had. It has 4,200 seconds of specific impulse, which is also about a third more than what the Dawn spacecraft had. What's interesting about those numbers is that means that if you just have the engine in standard gravity, the engine does not have enough thrust to overcome gravity.
Yeah.
Just by the engine. But what you've achieved in real life, more thrust than mass by quite a bit, because you have everything else that's in this on top of the engine. Yeah. So clearly, while these engines are similar, what you're doing is different. So, what's different in the structure of what you're doing compared to a Hall effect engine?
The structure of mine, it does have a large surface area. especially large surface area for its weight. And it has very long collector emitter surface. I mean, it's got 8 rings, and the outer diameter is 50.5 inches. And so these 8 rings, if you put them all together end to end and straighten them all out, it would be about 60 feet long, a collector. And maybe it doesn't sound very scientific to use empirical.
Yeah, we're very metric over here, but we're also good at converting from imperial, so I think we'll be all right.
20 meters. Okay. So yeah, it's like 20 meters of collector surface, and that weighs just a few grams. The actual aluminized plastic weighs 2 grams, 2 or 3 grams with the glue and all. And then you got a structure to support all that material because it's very lightweight. It just all kind of adds up faster than you would expect too when you're building it in real life. Anything you put on there, you have to take into account how many milligrams you're adding. So, but structurally, the emitter wires on this are 6 inches high on this one. The lifters have usually, 2 centimeters high. So 6 inches is, I have to figure out how many centimeters, 2.54.
Right, so that's about 15 centimeters.
And that's more efficient if the structure is light enough, and if you use thin enough, crazy thin emitter wire, and if you have a low current power supply, it all works as a system. It's like a computer. If you put the wrong value capacitor in there, the whole thing probably won't work. Wrong value resistor, right? So,
and, what I've noticed in some of the missions I've done in the simulator is when you're really trying to optimize, you reach the point where things that seem really minor become really important. I'll be building something that's 100 metric tons, and it'll get to the point where I'm looking where I can shave off just tiny fractions of a ton and just 10 kilograms here or 10 kilograms there, and it starts becoming a significant improvement that you get excited about. So yes. I imagine you're at the point where even something really insignificant, like every milligram, I imagine really has to count.
I made a microgram scale with this real long metal rod, and it bounces on a razor blade. And I built it so that I could measure the weight of the drops of glue I was adding. Right? And so if you're adding thousands of drops of glue and each one weighs a milligram, it can add up. And so you add all that up, and that would seem insignificant. Who cares? Just slosh a little glue on here and there. What's the big deal? But it all adds up, so you have to be careful. And the emitter wires, they're 2.5 microns. People figure, well, this is thin wire. This is 5 thousandths of an inch. That's like looks like a hair. It's probably just fine, right? But it's not. It's those microns make a big difference.
What are you looking at next for optimization? Is there more weight savings in there, or better power supply, or
everything? Every part of it is getting better. It's a big chain of components, and they're all improving. I mean, I can't say all, but generally speaking, they're all improving. I'll tell you the secret that I got coming right now. I have some silver coated material, because right now the problem is that the aluminized surfaces, aluminum grows an oxide on it right away.
Right, kind of a protective layer too, though.
Right, and that oxide stops the oxygen from getting to the aluminum. Right,
so it's ionizing less oxygen because of this.
Yeah, I mean,
aluminum oxide layer.
It's not. I mean, it needs to be electrically connected to the ion stream, and it's not, because it's coated with a non-conductor, right? Aluminum oxide. And then all the connections in between those rings all have to be jumpered together. And to make them really reliable, I'm not sure it can be done with aluminum. I mean, it's really a major issue. So right now I have some silver-coated polymers coming. And silver has fantastic conductivity, and pure silver oxidizes very slow. It's not like sterling silver, which oxidizes much quicker. So it'll have a far better conductivity and very reliable connections.
So maybe we can get that 14 watts per gram up to 15 next, or what's the next goal?
I have no doubt that it will increase it. Well, I mean, there's always, you never know.
Right, you never know.
Until you do it. But I can tell you, at least it'll be reliable connections. If I fly it for 2 minutes and I switch it on, it will work every time. And I can adjust the steering. I'm balancing like when I change battery sizes, the center of gravity goes, the steering then won't work. So it has to be balanced perfectly to make the steering work. So I'm working on some adjustable means to make sure that the center of gravity is perfectly balanced.
You brought up steering. How do you control this thing?
Okay. I have tried all kinds of different systems. Let me just tell you a couple extra, things about it. I've tried several different hang glider steering type systems where you have a mast that swings. And early I had the circuit hanging under the craft, and I had a piece of muscle wire that would swing the circuit slightly. But that wasn't anywhere near good enough to make it steer without crashing. So then I got this, you know how a universal joint looks on a car?
Yeah. I'll put a picture up too.
Okay, cool. I had a tiny little universal joint with like a plastic, components. It didn't weigh much. And a friend of mine made it for me. He sent it to me. And I put it on top of the mast there. And it had two itty-bitty servos, extra small servos. And it would make that universal joint lean, in the four directions. In four directions, forward,
right,
backward, right, left. And so then I put the batteries would plug in on top of that.
So you're using mass that you already have, so you don't have to add more, which makes sense.
Right. So I would swing I'd go right with my transmitter, lever, and the batteries would lean to the right, and so on. But that again was horribly, you turn right and it would take it like 2 seconds before it would start to turn. So
I imagine you've probably crashed a lot of these over the years.
Over and over again. It's like, oh man, not again. You got to just rebuild it.
Right.
Fix it. So and every time you fix it, it looks worse. It's like a one of those stock cars they have all beat up.
A stunt car by the end of the movie.
I just keep rebuilding them as they bite the dust. And so then I tried a bunch of different. Of course, I've tried cutting it into sections on the top. This Seversky, Alexander Seversky, Major D. Seversky, made the first Ionocraft to lift itself straight up.
That was with the external power supply that was several hundred pounds.
Big, huge boxes. But he did make it fly straight up, and he disclosed in his patent that you could, just cut the power off to one side or the other, and it would lean that direction and fly in that direction. So I, segmented the top of the structure and hooked up some variable resistors. And I had to design that all so it didn't weigh hardly anything. And I was able to cut the power back to one side or the other. But the problem there is when you start cutting it up into sections, it makes extra corners. In any place you have an extra corner, the power leaks away. So, or some of the power leaks away. So it wouldn't fly anymore with too many, when it was segmented. So I tried with just segmenting 2 rings, right? And then I tried it with just segmenting the outer ring. And even doing that stopped it from flying. So then the next step, I started adding. So finally what I'm down to now is it's got, at 3 of the corners of the vehicle, it's got 2 extra V-shaped collector pieces. 3 corners, it's got these, they're extra V-shaped collector segments, but they're not sharp like a V, angle like a V. They're sort of much less acute angles because they fit in between the collector rings.
So instead of segmenting the main rings, you're adding something to that. So
yes,
this gives you less power loss overall.
Yes.
Okay.
Less power. I mean, I didn't disturb the part of it that works,
Right.
And I just added these little extra sections. They produce extra lift, but they're not as efficient because they have ends on them.
Yeah, I have experienced that before when you've started to spend enough time on a project and it gets to the point where you don't really want to change things that already work because sometimes they stop working in unexpected ways.
Yeah, every time I would change it, which is a lot of times, it would stop working. So I added these parts to it, and it actually seemed to increase the lift a little at first. And then if I add extra the very last video there has 3 extra V's on 3 corners, so it's 9 in total. And that one actually started to get weak in the structure because you don't want to have a 9-ring craft.
Right.
Weaken for some reason, and I've experienced that many times, so several times. So they keep it at 8 rings, it's strong enough to fly around and carry reasonable batteries. So it has 3 corners that can be attenuated, and I do that in a digital way now instead of an analog way.
So so what you're actually controlling is the resistance.
Well, yeah. I was, but then I had, it seemed like I had a resistor failure, and I had there's so many little connections that can arc and, malfunction. And the thing has to be so light to do that it's not, in real life, I found out, well, if you just shut the power on and off to a segment, right, you can flicker it at any rate you want, right?
So it's just on off, and if you wanted partial power, you're flickering it off and on?
Yes, that's how I changed it. So that all of them are normally on, and if I want to go forward, I shut off the front one, right? And if I want partial power, I can flicker it.
Now, are you controlling this all manually, or is there logic in this?
Right now it's manual, but I built a gyro stabilizer that has accelerometer and a gyro chip, and it's just 2 little chips that are it's a few little chips. They're connected point to point. There's no circuit board, so it's like it only weighs a few hundred milligrams, and that has been tested, and it does fire the 2 little servos so that it will stabilize the vehicle.
Right. I imagine with all the advancements in drone technology right now that there's probably some techniques in the control of those that could be borrowed from.
Yeah, for a fixed wing aircraft stabilizer circuit, basically.
Another thing I was curious about is this seems like it could have some serious implications on drones. If you could have a solid state drone, it could be quieter or maybe even more stable.
Yeah, more stable, more quiet, more I would like to think more efficient. It's not more efficient right now, but it's pretty, it's getting there. I mean, right now, I'm losing half my power in the circuit. Half the power is lost in the transformer, and it has an 11 millimeter diameter transformer right now, and that tends to get pretty hot. Yeah, I'm working on stuff like that. Those are the kind of problems you run into.
What are speaking of problems you run into, what are some of the oddest, most unexpected problems you've encountered over the years?
It's an odd thing, but it's not a problem. I put epoxy on the structure of the device is made of boron filaments. It's a very rigid black, filament, and very lightweight. That's what the structure is made out of. And the problem is the core of that is made of tungsten, very thin tungsten wire, and I really don't want the support structure to be conductive, but it has a little conductivity inside of it there. So I put a little dab of epoxy on the end of that filament to cover up the boron, to insulate it electrically. Right. And when I energize the craft, the epoxy that was wet kind of floats away from and sprays off the end of that rod in a very odd way. It's like you see epoxy spraying off the corners, like drizzling off into the air.
So you chose boron because it's presumably very rigid for the mass that it is. And
highest Young's modulus. They used it on the space shuttle to stiffen it. And, it's that's basically it, the stiffest thing by weight. And of course, there's a matter of if you make the thinnest wall tubing, you're getting more stiffness per amount of material. So it's not a simple thing, but that's worked best so far. So as far as odd problems with it, everything has to remain once you create your high voltage, your 50,000 volts, everything that comes out of the power supply that's at 50,000 volts should not be any closer together than the emitter wires.
Right, because then the current's going to go somewhere else other than where you're actually trying to get it to go between collector and emitter.
Right, it'll go right to that point like that. And another odd thing, crazy things. One time I was losing power. I couldn't find out where it was. I thought I had a broken emitter wire hanging down or something. And I found there was a little piece of emitter wire stuck on the collector, sticking up. And that was acting like a lightning rod.
Yeah, one of the things I'm really impressed by is there's so many factors here. You're dealing with a lot of very tiny things that I'm assuming must have very narrow tolerances. And you don't have an entire team of people working on this. You don't have an entire university department of resources or a company with resources behind you. I'm just shocked by what one person has been able to achieve here.
In a way, though, I'm not really doing it by myself, because personally, my family's been supportive, at least of late. They weren't as supportive in the beginning. When I need a good material, I call whoever's the expert. If I need boron, I call the best boron guy. If I need something aluminized, I call, I've talked with a lot of experts. So just use Google, and I'm sort of teaming up remotely with all the best people.
Still, if there's a problem, you're the one who has to figure it out. Yeah,
I figured out how to put the ingredients together, but I'm not the one that makes... I'm lucky I have access to so many wonderful materials, and, we have computers these days. It's just, if I have to calculate something, Google can do it for me,
You talked a little bit about this earlier, but I wasn't recording, and it was really interesting, which is the mindset at the beginning, when you first started working on this, before anyone had managed to achieve self-contained ion-propelled flight. What gave you the confidence and motivation to approach this seriously before it was clear that it was actually possible?
This was before I got my degree in electrical engineering, and I was working on as an aircraft welder, and I was fixing these turbine engines. And the guy, the manager said, "Well, they run at like 40,000 RPM, and that's about it." I thought, wouldn't it be cool if you could make an electronic jet engine? And I thought all you'd have to do is just have a bunch of magnets, a row of ring magnets, and if the air was sensitive, if you could make the air sensitive to magnetism, you could just fire them sequentially, and you could just go as fast as your circuit would allow. And I tried to make that, and I found that it was kind of rather heavy and didn't really work too well. And then I found the Seversky Ionocraft, and I just tried to, just for fun, to copy his patent in the year 2000, and it didn't quite fly. and then I made my own design, but it did swing around and it did blow a candle flame. Finally had this design of my own, which consisted of an aluminum foil with a bunch of round holes in it, and little needles that would hang over the pieces of wire that would hang over those round holes. And then when you energize the two surfaces, the air would blow from the needles down through the round holes. And I made that, and it was blowing air, but it wouldn't take off. And I was getting frustrated. I was about to quit, And I thought, what if I just switched the wires, And I had like a computer monitor to power that one. The flyback transformer from those.
The power supply out of an old CRT monitor?
Exactly. The old computer monitor tubes had a transformer that made high voltage DC, that made high voltage and would come out of there in the form of DC. So I had those wires hooked up to that thing, and I was about to give up, but then I switched the wires over and I put negative polarity on the emitting points, and I threw the on switch on the CRT, and the thing floated up near the ceiling. I was like, oh my God.
So swapping the polarity made a significant difference.
Yeah, going with a negative polarity on the emitters made it float up to the ceiling.
I wouldn't have anticipated that.
Yeah, I didn't either. I thought it was just not going to work, and it was a bad idea.
So you were at the I'm just going to try things because I haven't tried it yet phase.
Yeah. I think. I had a plan to make a thing fly, to make a thing work, and it didn't work yet. So I was just trying something else. Yeah, I was just trying things. So that thing would fly, and it balanced pretty well, and it was a fascinating device. I never patented it. But, it had a large external power supply. So then I got plans to power a flyback transformer without the television present, without the monitor, computer monitor or television. I used both. They're different, dependent.
So you were using the power supplies out of those because they were
only thing I knew
very high, like the high voltage you were looking for? Or?
they had the highest voltage of anything I knew that I could get, and there was a lot of junk ones you could get,
Which is presumably why they explode sometimes. I have heard about that.
Yeah, and they're dangerous. You
Yeah.
get a bad shock if you're not careful. But anyway, I experienced that.
Well, I was first thinking that I was going to suggest you try out Kerbal Space Program sometime, but I'm a little bit worried now that if you do, you're going to be a force to be reckoned with, and you're going to be breaking all our records and whatnot.
I probably wouldn't be that good with it. I probably wouldn't be that good at it, but super cool. Maybe a lot of people. I really like science fiction, and maybe a lot of science fiction or rocket scientist types. Really do Kerbal a lot. But so I originally I got this big screen TV to do it. That was before the computer monitor. Really big, massive thing that people used to get, and with a CRT in it. And then I switched over to a smaller monitor power supply, and then I got a circuit that had like 5 parts that you connect to a flyback transformer, and it allows it to run off a big battery. So that was a big step forward. And then I just kept, investigating every kind of power supply there was and trying to improve upon the best of what was available. And over the years, the power supply was reduced to just a few grams.
What was the point where you realized that this was actually going to work? Maybe not when you were done, but like the point where you figured that, okay, this is actually possible. And
it was going back and forth in my mind. It was probably maybe 2005. I'm just, best guess. About 2005, I had this device that was a hexagonal spiral. It was hanging from a postal scale, and I got it to hop, and the thread would go loose that it was hanging from, like completely loose, but it would burn out the transformer. And it's like I said before, I thought, God, it actually can lift its power supply, but it just burns it out after a few seconds. And if I shut it off quick enough, it wouldn't burn it out. So I thought I'll just make a little bit better transformer. And I tried all kinds of different windings, just made piles of different little transformers, and tried all kinds of different little voltage multipliers. I was using surface mount parts, so everything was very small scale, and a microscope to put them together. And I just realized that, I started getting longer hop, 5-10 seconds and stuff. And I could see, that it was going to, because there was so much heat in the transformer. So I realized with this Ionocraft, then when I was building it, that hot transformer represented a specific number of watts of power loss that wasn't getting into the lift.
Right, we're not trying to build a heater. So
yeah, exactly. So the hotter that transformer it is, the more power is there to be utilized.
Do you think if you were doing this in a vacuum, would you need some kind of active heat radiation?
That's an interesting question. It crossed my mind once a long time ago. I think that things don't radiate heat very well in a vacuum.
Not very well.
Yeah, so probably I would need a different heat management, thermal management system. Right now I'm using these thin sheets of pyrolytic graphite.
So if I can shift subjects a bit, I also wanted to look at future applications of this. If we're bringing this to space and we're bringing gas with us to use as reaction fuel, the really important thing to know would be specific impulse. Is this something you can calculate, or how would we measure this?
I'm sure it wouldn't take that long to figure out how to do it, to make that measurement.
Right. Well, if you can get a vacuum and test it there, and you're looking at the force, all you got to do is look at the the ratio between the force you're getting and the rate of fuel consumption, and that's your.
Wouldn't it be proportional? I mean, if you're getting 27, if you're getting 14 grams of thrust per watt, right?
Right.
Which is what the structure of my craft, roughly speaking,
Right. So 14 grams per watt of lift. Do you know how much? How much mass of gas you need per watt that you're using? Is that a known figure?
I'm only going by what the Dawn spacecraft used.
Because the Dawn spacecraft was 3,100 seconds specific impulse.
Okay. I think that my specific impulse is much, much higher, but I really, truly don't know. So, but again, don't you think that the watts per gram, wouldn't something that can produce 14 grams of lift on 1 watt have a higher specific impulse than something that can produce, that takes thousands,
Not
more per watt?
I think not necessarily, because what that's measuring specific impulse is, it's measuring the ratio between the propellant used, which in your case would be oxygen or nitrogen or whatever you're ionizing, and the force you're getting. And it could be that as you're increasing the grams per watt, you might also be using more gas as well.
Right.
So I don't really know the answer to that.
Right. Well, it could be going the opposite way.
It could even be going the opposite way, right?
I could be wrong. I'm not claiming that I know everything, There are several things here. Number one, I'm accelerating with much higher voltages, right? Which should make the particles go much faster.
That's a really interesting idea. I don't know what voltage the Call effect thruster in the Dawn spacecraft uses.
1,000 volts, right? And this is using like 40, 50,000 volts at least.
So you're thinking that it could be possible that this higher voltage is increasing your specific impulse, perhaps dramatically.
Dramatically, yeah. And if it weren't moving those particles faster, how could it be producing more lift per watt? Well, because it has more propellant flowing in, right? So if you move a lot of propellant slowly, you get more lift.
Right.
So I think it's sort of a combination of those concepts, those two particular concepts.
Well, I think this needs to be tested.
If you put it in a vacuum, you could say, well, for one thing, for sure, I can tell you when you put these in a vacuum, what happens is as you pump the air out, the current draw goes way up. And that's because there's less air, and the air acts like a big resistor. And as you remove the air, the resistance goes down, and that causes the current draw to go up, which is counterintuitive to non-electrical engineers.
Right.
But so what happens is the current draw, there's less particles flowing through it, and the current draw goes up. So what people should do is raise those emitter wires much higher, and then it should increase the resistance again, and the current draw should return to where it was, and the available particles would return also in a somewhat thinned out atmosphere.
Is there a point where you'll consider yourself as having succeeded here, or is this just an ongoing challenge to make this as good and as efficient and as powerful as you can?
Well, I have goals. If it flies across the yard and the steering's really good, and it's very stable and it can hover, I would feel that that's quite a milestone, a goal, one of the goals that I have. So I don't feel like there's a beginning and end. I feel like there are just milestones that are important,
Gotcha.
that would give me a kick, And one of them would be to see it, go up into the sky and go up near to the clouds, or fly around the neighborhood, or be able to make one in a few days instead of a month, or if I could turn it into a product, that's going to be. I think that's a commercial product. I think that would be. That'd be hard not to say as a.
You've preempted my next question, which is, when can I buy one of these and how?
I'm trying to expedite that as fast as I can, But I mean, as long as it's got bad connections, or it's so fragile, you bump it with your shirt sleeve and it's gonna malfunction. We can't have that. It's got to work every time.
Yeah, it's got to be user proof.
Yeah, user. Well, I mean, I understand if it's really just for adults and it takes a little care. That's one thing, but it's got to be. Right now, it is very fragile. It's very light, and it takes a lot of care just to keep it going.
Okay, I think that's everything. Unless there's something that you're burning to mention, or something you want to talk about, or.
This is the most thorough interview I've done yet. I mean, you see my logbooks, right?
Yeah.
There's
I didn't think this was going to go as long, but this was just fascinating.
So I appreciate this very much, and I really enjoyed talking with you, and I hope that this can help some inventor out there that's trying to to do
I
this.
hope so. And I think definitely, I think this is just going to be interesting to a lot of people and hopefully educational too. Thank you, Ethan, very much for your time. And thank you for sharing your knowledge and experience and your enthusiasm for this. To everyone, thank you very much for watching. Please let me know what you think. If there's interest in this, I definitely would be interested myself in doing more videos on Kerbal real-life engineering connections. Talking to Ethan and learning more about Ionocraft was an incredible experience for me. Thank you again, and I'll see you guys in the next one.